Hey, welcome to CAN Bus Communication Part 2. Now, if you missed Part 1, that's where we went through Step 1 of our process. And Step 1 of our process was communication networks. Now, what we talked about was these big modern day communication networks and how we have to break them down into smaller, more manageable networks so we can actually diagnose them. We also talked about why we broke them down and the advantages that had. And it wasn't just for us diagnosing them, it was for the car. It made the car more fault tolerant, I should say. But now that we have our big communication network and we have it broken down into our smaller network, our smaller section, we have to focus on Step 2 of our process. And that is looking at the network topology, or the way the network is wired. Because even if we're just talking about CAN bus, there's numerous ways it can be wired. And if something is wired differently, then we have to test it differently. We're also going to look at Step 3 of our process today, and that's going to be looking at the protocols or the languages. And this is going to be, well, what is being spoken on these wires? What kind of communication is taking place? What voltage should we look at? Because that's another thing we need to know before we start testing anything. But we can't get to Step 3 without Step 2, so let's get right after it. Now, network topology. Now, this may be a term you've heard before, or it may be new to you, but if you haven't, you're going to hear it a lot, because this is the term that we use for how the networks are characteristically laid out, how the wiring is laid out. And the easiest way to describe that is to look at our old trusty network diagram. And this is the network diagram that we looked at in the first class, and we're going to keep looking at it. We're going to keep building off this diagram, and hopefully, if I do my job correctly, by the time we get done with this class, you'll be able to look at this and hopefully see it just a little bit differently, or at least get some more information out of it. Now, in the first class, we looked at this, and we've seen that it was one big network. And we also seen that it was 4 smaller networks in one big network. We also talked about the DLC and how the DLC isn't our go-to spot to test anymore because a lot of times it goes to gateway modules and how that can block us from the network. But what we didn't talk about was how this thing is wired. Now you may be looking at this and saying, well, maybe he just likes to play with different shapes or write in different colors, which maybe I do. But they're wired on here for a reason. There's a reason why this green network looks like a circle here, and this red network is kind of a box with some legs coming out of it. And look at our 2 CAN networks. I mean, it's pretty obvious to see just by looking at it that they're wired completely differently. And like I said before, if they're wired completely differently, well, they got to be tested differently. And this is why this is Step 2 of our process. So there's 3 main topologies out there. We're going to talk about some of them more than others, but anything you look at is normally going to be one of these 3 or a combination. So we have our ring topology, which is no surprise, the circle. Looks like a ring. We have our star topology, and everything comes to this point here and it looks like a star. And then we have our bus topology, and I like to think of this as just a little bus bar here, and all the modules go to that. So starting with the top, let's break these down just a little bit more. Now, ring topology is not used much anymore, but it's still out there and you still might see it. And like I said before, when we do CAN bus communication, we have to understand everything around it and the whole network. And I want to talk about this because we still might run into it. Now, right away, looking at this, and you can see we have our modules here. And each module is connected to the other module, kind of like a little daisy chain here, and it creates a ring. But what's really unique about this network is, or this topology, is when it's used in a car, it's normally used in a unidirectional fashion. And what I mean by that is the modules communicate in one direction. And why that's unique is because most communication networks don't communicate that way. What else is very unique about it is there's normally a start module or a master module. And how I like to describe this is it's kind of like a relay race. You have one person at the starting line with the baton, or you would have one module at the starting line with the microphone. And it goes to the next person, or the module talks and it gets to the next person, and then it gives them the baton. And now it's their turn to talk, or it's their turn to run. And it keeps going in a circle until it gets back to the finish line. And then if it starts again, it always starts at the same person. And that's exactly how this network talks. Now, like I said, you won't see this much anymore, but here is where I see it most of all. And I'm bringing this up so if you run into it, you can identify it. Now, here's an example of a MOS protocol. And this is a media protocol, and this is normally where it's used. And you can see we have our master module, and it's communicating in a circle here. And this is our ring topology. Now, this one is a 2-wire network, and let's look at some of the things about this that might make it weak, I should say. If we want to add another module to this network, let's say we want to add a module here, you can see that we have to change the wiring of the whole network. And if we think about faults with this kind of topology, let's say we had a fault right here. Let's say that wire was cut. Well, if this is the module that starts all the communication and it only goes in this way, it's kind of like that house of cards. The whole thing is taken out. And I'm pretty sure that's probably why it's not used anymore. Now, it does have some of its advantages, and there's a lot more information on ring topology and stuff like that, but since it's not used in CAN much, I'm not going to spend too much time on it. I just want to make sure that you guys can identify it. So let's get into star configuration. Now, this is my all-time favorite, and it's probably the configuration that's used the most today in topology. And if we look at this, we can see all of our modules are just kind of going to this center here. So it's much different than the other one. And you can see, since they're all going on their own wire to the center, it's more of a parallel wiring than a series wiring. So now, if we want to talk on this network, it talks down to the center, and you can see how they all communicate together all at one time. So if this guy says something, it comes down the line and everyone gets it. What else is unique about star topology is, let's say we want to add a module. Well, we just go to the center. You just go to the center. And that could be pretty handy in today's cars because we have so many different module options and so many different car packages that if we have to add modules or remove modules, it makes it so much easier. And what if we're diagnosing something with a star CAN? Well, now let's say we think this module is shorted or this wiring's bad. All we have to do is find that junction connector or that center, and we can isolate it. Or we can test everything from here. Now, one thing about this is normally it's not going to be in the center of the car and look like a star like I have pictured here. Normally they're going to put a junction connector, let's say like in the dash here, or maybe it's in the rear back seat. So if we have all of our modules, say there's a module here, 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 and here, now it just gets wired to the star. Why else is this such a good thing? Because if, let's say there's 20 modules on this network, God forbid, but let's say there's 20 modules on this network, if we need to test it, now we just have to go to that star connector. We don't have to go and find every module. We can test every wire from there. Let's look at what it looks like on a wiring diagram. Here's our splice pack. This would be our star connector or our junction connector. And here's all our modules. And they could be all over the car, but they all go to one central point. And let's talk about the options again. Here's rear wheel steering. I've never even seen a car with rear wheel steering. I've seen one on a commercial, but they're out there. But if it doesn't have that option, well then this is RPO, then it's just not wired to the star and they don't have to change the whole configuration of the network. Get rid of this here quick. Now let's say we have a problem with this type of network. Well, let's say we test here, we have a problem with this bus and it's shorted to ground. It's straight ground. Well, now we don't have to go to every single module and unplug them or test the wiring at them. We can go to our junction connector and we can remove one module at a time. And let's say it's the engine and brake control module. And once we disconnect it, it goes away. So now we just have to test our wiring to our engine brake control module. And if it has this RPO code, we have to test this one. But it sections off our network even farther. And we only have to locate one thing. This is why I like this star configuration so much. And this is probably why it's used so much. But you also can see how this topology just to the ring is so much different. And this is why it's our second step. Because if we had this one or the other one, we're testing it differently. Let's look at our bus configuration. This one's even more different. It shows this bus bar here with all the modules going to it. And this is very commonly used with CAN. So most of the time CAN's 2 wires, so it would look something like this. Now, here's where little confusion comes in place. This is a picture, or this is a wiring diagram you're going to see a lot. And it's used in a lot of CAN bus training, it's used in a lot of factory wiring, and it's used in a lot of training manuals. And the reason it's used is because it's very easy to look at. I mean, this makes a lot of sense. We have our lines and each module just goes to here. And it's great for CAN training. The problem I have with this is so many people train with this wiring, but rarely any cars are actually wired like this. I mean, do you really think there's 2 big wires going through the middle of your car that these modules just get connected to? No. But it's easy to understand what CAN is with this. But we're here to diagnose it. This is how most CAN's actually wired. Either in a series CAN, and I like to call it a train bus, because it looks like a train, and it acts like a train. I call it series because it's wired in series. It's a straight. Everything's wired together. And I call it a train bus because if we want to add a module, it's just like adding a train car. We have to add it to the front or the back. Or in the middle, but we'd have to separate it. And if we would disconnect it, let's say we disconnect it here, it's like disconnecting a train. Everything on the other side of it we lose because it's wired in series. And you can see that looks nothing like that other diagram I showed you. Now look at this is the other way, and this is how most CAN is wired. Star CAN Bus. And I don't know if Star CAN Bus is a thing, I've heard it, and this is what I use. But this is more of a parallel wiring. And you're looking at this and you're going, this is the same wiring you just showed us, you just put a dotted box around it. We're not fools. We have to pay attention to the dotted lines. Even on the Star CAN Bus, or the Series CAN Bus, and we'll talk about that one next. But why I put a box around here? Because this is how CAN Bus is normally wired in a car. And this is the exact same wiring, just how it's wired in a car. But why do you think people don't train with this, or they don't show you stuff like this? Because it's hard to look at. It's much harder to look at. There's all these wires crossing each other, but this is the same thing. And this is how we have to think about it when we're diagnosing a car. Let's look what it looks like in a car. Why do I call it Star CAN? Because it's exactly the same as Star, just 2 wires. They should call it 2-wire Star CAN. They shouldn't even call it bus. And Star CAN Bus. Be careful with that word because we use it for small networks and for topology. Go figure. So when we're diagnosing a car, and we see that first diagram I showed you, and it looks like there's 2 things going through the whole car. When you have a problem, what are you going to do? You're going to be thinking, where are those 2 big bus bars? But what we really have is these star connectors, these junction connectors. And no, it's not the size of the engine. Normally, like I said, they're here or you'll be under the seat. So now when we want to diagnose this thing, we just have to find those connectors. Look what else we can do. Here's a car with 2 buses. Let's say this is CAN 1 and CAN 2. Well, we have to go with step 1 now, right? We have to break down the network. Let's say we can't communicate with number 2. Let's get that car out of the way. We can't communicate with number 2. We already know we can't go to the gateway module. We talked about that. But now we have these star CAN connectors. So what are we going to do? We've isolated the network. We've broken it down. Now we know it's star configured. Star topology. We can just go to our network. We go to our little junction connector, our star connector, and now we can test each wire separate, or part of the network separately, the high and the low. And we can isolate it. We can test every module's wire from there. So let's say the orange wire, here, let me get this out of the way quick. Let's say the orange wire is CAN high, and CAN high is shorted to ground. It's straight to ground. Well, we test here, it's still straight to ground. Well, now we can remove each one of these until we find out which one's shorted to ground, or we can test them differently or separately. Normally what it is, it's all the pins like this, and then the connector links them together. So when we remove the connector, we can test every wire separately and see which one's shorted to ground. And if it's this module right here, we've just took this whole thing and all we have to do is look at this wire. And when you look at this, that wiring doesn't look anything like that first one I showed you because that's not how it's actually wired. It's just good for teaching. But we have to think about how it's wired in the car to have success. Even if it doesn't have a gateway module. And I know I've been beating this gateway module thing into your head, but not all cars have it. But we still have to break it down first. Let's say we break this down. It doesn't have a gateway module, but it still has 2 CAN buses. Or 1 CAN bus. And now we have 1 big bus. And we talked about that as like a big house of cards. Well, now we wish we had a gateway module, right? To break it in half. But we don't need it. We have our junction connectors. So now we can get to our junction connectors, we can break the network in half too. Or by ourselves. Let's say this blue wire is shorted to power, or blue part of the network. Well, let's isolate it, see which side it's on. Once we know what side it's on, we can isolate it even further, 1 wire at a time, from 1 location. So this could have, this showing 12 modules on this network. It could have 50, who cares? Because we only have to go to 1 location, and we're going to test each wire separately. It doesn't take much time once we're there. And we don't have to worry about tearing the whole car apart. I've seen people tear the whole car apart, going to every single module, when I'm like, there's a connector where all the wires meet up. That's where we need to go. And that's why we need to look at topology. And the reason I make these pictures is because this is how I visualize it in my head, and I want you to visualize in your head, because when you look at a wiring diagram, this is what you're going to see. This is the same wiring that you just looked at in a wiring diagram. Here's the DLC. Here's the CAN high and CAN low. Here's your junction connectors. And then all your modules. And we're going to take the same process. If this wire is shorted to positive, well, then we're going to find here, and we're going to isolate the network, and we're going to see if it's still shorted to positive. And then we're going to look at the wire, and then if it's gone, now we just have these 3 wires, and we're going to test at our junction connector for each one and see which one it is, and we can quickly isolate it from getting to 1 spot. And we can do this because we know what topology it is. And the other reason we need to know what topology it is, because what if it's this topology? This is the other one. This is commonly what GM uses. They're everywhere. That's way different. Are we going to test that the same? No, this isn't series. And what did I say about the dotted lines? We have to pay attention to dotted lines. Another thing that people understand about this bus, well, 1, it's different. 2, it's in series. But these wires right here, they're actually going through the modules. And not literally through the modules, but the circuit is always together from pin to pin inside the module. So think about these wires as going through the module, and the module connects to it with a little chip like this. So when we're testing these, so let's say we lost power to this module and it's not turned on, it's not going to take the network down. And we can still test, and we're going to talk about these resistors too. I'm sure there's some people out there just screaming about, well, the resistors, you got to watch out for the resistors. We will talk about that too. But this is how this one's wired. And it's different. But as long as we know how it's wired, we can test it. Let's look at what that looks like on a wiring diagram. See the wires? They're going through the module, and here's a little communication. But you can also see it looks like a train. If we have to add if you have to add a module, we'd have to come off the back of a module, like right here. And if we cut the network in half here, it's just like cutting a train in half. We lose the other half. So can we go to those junction connectors? No. Let's look at what it looks like before. Here's the same thing, but in a different series, or in series CAN, not in parallel. We have a problem. We can't talk to the stuff on CAN 2. We know we can't test from here. Well, we know we can't go to junction connectors because they don't have any. And we can't just start disconnecting modules because, well, we're going to take on the whole network disconnecting modules. So it's wired differently. We have to test it differently. We remove the car. So we'd have to, let's say we're testing this one, we'd have to jump the wires if we took the module out. And there's other ways to get around, so I'm going to show you a trick in a little bit, but you can see just how important topology is. And I really want to show you this too, because this can be super confusing. In the last class, I told you that we've got to look at modules because sometimes they can communicate 2 different languages. Well, when we look at series CAN, what did we have? we had the two CAN wires coming in, and we had the two and going through the module and coming back out. Now it's not an input and output, remember, they go through it, but what would that show you? Well, it would show you this. Here's 4 CAN wires. Must speak 2 languages. Not on this one. Look at right here. 1. High-speed CAN 1. So we have to look closely. That's the wires coming in and the wires coming out. It would look like this inside. So we have to know this. So if we unplug this thinking we're going to test the wires, we've just took everything down the road from this out because it's wired series. Look at this one, 9 and 9. Now it does have low speed CAN, so this one does speak 2 languages, but you're going to see 5 communication wires there. We can't be fooled because now we know what we're looking at. And now let's look back at this wiring diagram that I showed you guys before. This is good for teaching. This is what you're going to see all over the internet. And it's great because I'm not saying it's wrong. It is, technically the wiring is right and it's great for teaching. It shows the modules in parallel, it shows the resistors. But what I've just showed you before, you can see that's not how it's actually wired in the car. So we have to think about it a little differently when we're actually diagnosing it. Because if we think about these as 2 big bus bars, it throws us off. So that's why we have to look at the topology. And here's a perfect example. Now, this is like my case study for this one because I've got burned on this car. And this is a Subaru wiring diagram. It's OEM, and it's an actual in the testing procedure, and it shows this wiring diagram. Well, immediately, what does this look like? Here's our big bus bars. Here's our modules coming off of it. So, yeah. They're showing it look just like our training. But what did I say? We have to look at the dotted lines. What do we have here and here? Junction connector. So are they going to some bus bar that goes in the middle of the car? No. And what else do we see here? And this is why I always say most cars and the majority of cars, because I never use absolutes, because as soon as I do, they change it, or somebody proves me wrong. This one proves me wrong too. Where's our junction connectors here? These things are actually spliced into the wire, just like that wiring diagram. So what do we have? This is a car that's using 2 different topologies on the same bus. But we're not fooled anymore because we can see it. Look what it looks like in a wiring diagram. Here's our junction connectors. This is probably CAN high, CAN low, front right side of dash, so they're right next to each other. That's where we test from the front of the car for the bus. And then here's the 2 behind the rear seat. Makes sense. Star CAN bus. The other side of the network are spliced together. This is good stuff to know before we start testing. This is step 2. And as much of a pain it is, we can't change it. Unless you're an engineer, engineering cars, and if you did this, I want to know why. Can you please comment? I would like to know why. And it doesn't really matter though, because we know how to find it and we know what we're dealing with. Here's our 2 topologies again. And now I need to bring up those resistors because the resistors are important. And there's probably people screaming out there about the resistors. So let's start with CAN. We're also going to talk about how the communication travels and how it doesn't travel in a circle. Because when you look at this, it kind of looks like a circle, doesn't it? It kind of looks like these resistors create a circle. But when these things communicate, this is 2 separate wires. Let's say this is CAN high and this is CAN low. And they each sit at a different voltage. And when they communicate, they change the voltage on the communication line. And remember, these wires go straight through. They go straight through. So let's say this module is communicating. As soon as it changes the voltage on this wire or this wire, it changes on both directions because it's on the line and everyone sees it at the same time. So when they communicate, it's going in both directions at the same time, high and low. So why those resistors are there is as the communication comes down the line, it's going to get to the end of the line. And think about those resistors as like baseball gloves. The module data communications can come flying down the line, and if it hits, it's going to come bouncing back. Because when you're thinking of this communication, you're thinking of it as speed, like how fast it's going. This is happening, this is humming. This is switching so fast you can't even comprehend. So if we didn't have those resistors here as like absorbers, the communication might bounce back and you'll get like a data collision. It's almost like two people yelling at each other right in their face. You can't understand anything. So while it looks like they're connecting the network lines together, and yes, they technically are, those are in there because the communication flows in both directions, one, and two, when it gets to the end of the line, it needs to be absorbed. That's why they're always on the end of the network. Now, the other big thing we got to talk about when we talk about resistors is they need to be in most networks to communicate. So let's pretend this is our DLC, right? And let's pretend we're trying to talk to the network and the network is down. Well, we can't just cut the network in half here anymore. Even if we would jump, let's say we cut the network in half here, even if we jump these wires together, because we need those resistors in there. So if we cut the network in half on this, it's like a series, it takes the whole network down. But there's a trick we can do. When we're working on series CAN like this, if we want to take this module out, we can jump these wires together, one. But remember, we can't jump the resistor, or we can't remove the resistor. So if we get to a spot where there's a resistor, or even if we're here, what I like to do is, here's a CAN resistor. This one is out of a GM. I bought this thing off Amazon for like 20 bucks. And I'll put the link in the description in case anyone wants one. And you can go to Radio Shack and get one. It doesn't really matter. But this is a 120 ohm resistor, and this is commonly what's used. And it's not what's always used, but it's commonly what's used in almost all these CAN buses. So if we have a resistor here, how can this be beneficial to us? Well, if we have a problem, we can cut here. We can wire our resistor in here. Or if we have to disconnect this module and it has the resistor in it, we can just wire our resistor in there. It's like, if we think of this like the train, it's like our temporary caboose, right? This is what we can use to go down the line of the network and just wire it in so we can isolate parts of the system. Why else I like this so much is because let's say this module is $1,000 and I think it's the problem. And it's not the resistor inside it that's fault, it's shorted inside. I can put this in here and make sure the rest of the network's okay before I pull the trigger on this module. Let's look at the star CAN bus. Same thing. Now this network, we can actually disconnect this stuff because we're not pulling the end resistors out of the network. But if we have to pull out a resistor, we can just replace it with one of these. Simple, right? Isn't it funny? We're doing this high-tech CAN bus communication and the only tool that I'm going to push to you guys is a $20 resistor. It's super helpful. It will help you diagnose this stuff because that's about what these resistors do. They absorb, they isolate the network, but they also bring it together. So when we do this stuff, just make sure you know where the resistors are, and sometimes it's hard to find. And if you have to pull a part of the network out, you either have to bypass the module on series, or you have to jump a resistor in if you're missing a resistor. And this can save you a lot of time. So let's look back at our original diagram now. Now when we look at this, what do we see? Well, when we first looked at it, it was just a nice drawing that I made. But now we see one big network with 4 smaller networks. But now we see this network in a ring topography. And we see this one in a series CAN bus. And we see this one in a different CAN bus with a junction connector looking, so it's probably a star CAN bus. And this looks like just a regular star. So now we know, if we isolate it to one of those, we know what it is, how it's wired, so we're ready to test it, right? We're ready, let's go. Not yet. There's one more thing we have to know, right? If we're gonna test here or here, what are we testing for? What are we supposed to be looking for? I don't have the multimeter yet that tells me good or bad communication, so we have to know what voltages we're looking for or what are lab scope patterns, and that's why we're going to get into protocols. Now, protocols are, I like to think of them as like the language of the network. What is spoken on the network? And it's really how the data is transmitted. So let's start out with what is data or what is protocol in the first place? Well, modules communicate with binary code. And what binary code is just ones and zeros. 1, 0, 0, ones and zeros. So let's say the engine control module is telling the instrument cluster what the coolant temp sensor is. Now there's voltage in these lines, but how they actually communicate is just 1, 0, 1, 0, 1, 0. That's as simple as it is. There's nothing more crazy than that. So how does it create ones and zeros? Well, it creates it using voltage changes. So a module has two modules together, right? And you have a line going between them. Well, that line is going to sit at a certain voltage. Now this could be 0 volts, it could be 5 volts, it could be 12 volts. And the module is either going to pull the voltage high or it's going to pull the voltage low. And when it does that, it's going to interpret it, the other module is going to interpret it as 0, 1 and a 0. Let's look at this. So let's say this one starts low and it's interpreted as 1. Now the module is going to pull it high and it's going to be a 0. And it's going to bring it back. It's going to be a 1. And it's going to pull it high for two time periods, and it's going to be 0, 0. And it's going to pull it down again for 0, 0. And its voltage is just going up and down really fast, and that's all we're going to see. But the module sees it as 1, 0, 0, 1, 1, 0, and it knows how to decode that. Some people actually use their time to figure out how to decode that. I don't care about that, but if you get into that, good for you. Here's what it looks like on a lab scope. Really fast. This one starts at around 0 volts, and it goes up to about 7 volts. But it's just going 0, 1. It's just going up and up and up, and it's getting communicated as 0, 0, 1, 1, 1, 0, 0, 0. So that's what a protocol is. That's all it is. So what's the difference between the protocols? That's simple too. There's 3 main differences between every protocol you're going to see. There's going to be the speed. How fast can the stuff be transmitted? How fast is it talking? How much data can be transferred in a certain amount of time? The signal voltage. And when I mean signal voltage, it's what does it start at and what is it pulled to? Is it pulled up or is it pulled down? And then the other one is wired. Is it a 1-wire? Is it a 2-wire? Or is it one of those new fancy ones that goes off fiber optic? But that's literally the only differences between the protocols. So the next big question I always get, and the next couple slides are going to be interesting because there's a lot of really weird information out there. But the next question I always get, so what are the protocols? And I was doing some research, and I constantly find this all over the place, and it's very confusing to people, and that's why I have to set it straight. We keep getting this thing that says there's 5 OBD2 compliant protocols. Now, yes, there is 5 OBD2 compliant protocols, but what is OBD2? Onboard diagnostic. So there is 5 compliant protocols, but it's for the diagnostic connector, not for module to module communication. So what I'm trying to say is there's a difference between communication from the scan tool to the diagnostic port and the modules to the modules. Let me explain a little more here. So this is another thing that we see all over the place, and this is kind of outdated information. Now it's not bad to know, but it might not help you that much. So pre-2008, in 1996, the government said everyone had to have an OBD2 connector port in the United States. And every OBD2 connector port had to use one of the 5 protocols to talk to a scan tool. So let's say GM was going to talk with their class 2 protocol to the scan tool. Well, that was this. And if they did that, they had to do it on pin 2. And it was okay because they had an OBD2 port and they were doing it on the right protocol on the right pin. And Chrysler or some of the European stuff was like, well, we're going to communicate using OBD2 port and we're going to use KLine. And that's fine too. But that has to be on this pin. You can see how everyone had their own pin. Well, in 2008, the government said, enough of this. Everybody has to use this port and everyone has to talk CAN on 6 and 14. So that's where a lot of the standardization came from. But the problem is, like I said, this is only for the car to the scan tool on new cars sometimes. There's a difference. And all these other ones are free-for-alls now. And why I'm bringing this up is because there's going to be a lot of times when we're going to have communication issues with a car. And it's, how do we know there's not a communication, or there is a communication issue with a car, right? Well, we know because our scan tool doesn't communicate. I don't speak computer. You don't speak computer. So when we're diagnosing a car, the only way we know it doesn't have communication, like if the car's dead, it could be a dead battery. It could be a blown fuse. We know it's a communication issue when our scan tool tells us it's a communication issue. But the problem is sometimes the car doesn't have a problem. the scan tool to the car has a problem. Let's look back at our Cadillac. So the only thing standardized now in 2008 is 6 and 14 have to speak CAN. And 6 and 14 are speaking CAN, but it's speaking the serial gateway module. So if our scan tool has no communication, we automatically think the car's down or there's a car problem. And this is the only thing that's standardized right here. And if we have a problem with our scan tool talking to the car, couldn't the problem just be in here? And everything behind here is fine? We have to keep that in the back of our head. And I'm going to show you a case study that's going to make this make more sense. Now, here's an old one. And it's old to show you how long this has been going on and how this one burned me pretty good. We have a 2001 Jetta. And this car's already, what, 22 years old, 23 years old? And it failed a vehicle emissions test. And in my county and state, you have to bring your car in, they plug it in to the OBD2 port, and make sure the IM flags pass. And if they pass, you're allowed to drive your car or register your car again. This one failed because the machine wouldn't communicate. So the guy brings it in and he goes, well, they said I failed, but I have no check engine light. I have no issues, no symptoms, but they just said it failed. So I look and I'm like, it says it didn't communicate. So I look at the network, let's break it down. And the first thing I see is all these wires are two wires. So they're a CAN bus. And then I see the CAN bus going to the DLC. And I thought, interesting. And the modules can still communicate, but let's look closer. There's also another wire going to every single module. So they speak two languages. And this wire also goes to the DLC. So every module on here speaks two languages. Why? I don't know, because that's what they wanted to do. So I had to do a whole bunch of research, and I finally found out the car uses CAN communication for module to module, but it uses the KLine, or a different communication on a whole different topology for scan tool communication. And it was okay because it was standardized. So you can see that scan tool to car communication can be different than module to module communication. And we have to know this, obviously. I mean, you don't even have to explain it. It makes sense why we have to know this when we're diagnosing this stuff, because we can get in trouble. And that brings me up to this point, which I really need to bring up. This is something that kind of burns me still, but as cars got more and more sophisticated, they started becoming risks. Because now we have a lot of personal information on our cars. Our cell phones are connected to them. And cars started getting in trouble because people learned how to essentially break into them with computers. So what they did was they decided to start using the gateway module as a security module. And Chrysler is one of the first people to do this. And what this means is when you put your scan tool on here, it's going to go right to the gateway module, just like we talked about. But now the gateway module is going to be like a security guard. It's going to go, stop. It's only regulated for them to allow you to talk to the powertrain stuff and certain stuff on the powertrain. But they have now put a security on a lot of the other networks. So if you want to talk to the radio or something like that, your scan tool won't communicate with it. And there's not a problem. You actually have to go to their website and you have to fill out information and tell them you're not a crook. And then you have to pay them a little bit of money, and then they give you a pass, almost like a ticket. And now they're saying, all right, now you can come in, and now you can talk to these modules. So your $13,000 scan tool that you have doesn't even talk to half the modules on some of these new systems, because the gateway module is now a security module. And this is another thing we need to know. And as mad as we are about it, and as mad as I am about it, we can't change it. So we just need to know that. But now let's get into some actual protocol stuff. And we're going to talk about CAN Bus, finally, right? And you know the funny part is, this is where most classes start. This is where most CAN classes start. You know how much information we covered before we even got to this CAN protocol? And if you've been following along through this series, I hope you understand why. Doesn't it make so much more sense that we know all this information before we start talking about this? And we're not even going to talk too much about this, but we need to know what this is, and I'm going to show you just some of the different protocols. So the CAN bus I'm showing you here is the standardized CAN bus. There's more than one CAN bus, and I just want you to know that too, so you don't think all CAN talks like this. Now, the first fun thing I want to point out is all these different names, because everyone's got to be different, right? So when you see it on a wiring diagram, everyone has to make its own name up. We got GM LAN, FCAN, LAN CAN, HS CAN, CAN C, and then Toyota's like, hold on, multiplex communication system. Great, right? So just be aware that they have a lot of different names. Now, CAN C, or the high-speed CAN bus, also communicates at a whole bunch of different speeds. Now, I'm throwing this in there just to throw it in there. It's not great information, but some people like to know it. Now, at the time I filmed this, one of the fastest CAN bus networks I could see was about 5 megabytes. If you're watching this later, it could be 5 times that by now. It's moving very quickly, but they typically operate about 5 kilobytes per second. Now, for a comparison, common internet speed, like the cheap internet that I pay for, is around 100 megabyte speed, which means it's still 20 times faster than some of the highest stuff that cars can speak on. But here's what we really need to know. Here's how it communicates. So CAN uses 2 wires, or this type of CAN uses 2 wires, and they both sit at 2.5 volts about. So that's what our resting voltage is. That's our protocol voltage. And when it communicates, the high voltage goes up, or the high wire goes up 1 volt, and the low voltage goes down 1 volt. And they do it at the same time. So they're essentially speaking the same thing on 2 different lines. One goes up and one goes down. And they do this because it makes a cleaner signal. It helps cancel noise out. That's also why you see that they always have their wires twisted together, because it's for noise cancellation. And by noise, I mean like electrical noise. So they normally sit at 2.5 volts, and CAN high goes up a volt, and CAN low goes down a volt. And that's what we'd be looking for when we're testing. But since they speak binary code, it would look something like this. So it would start at maybe 1 volt, or a 1, 2.5 volts. It starts at 2.5 volts, but it'd be like a 1 in the protocol. Then it goes up, down, 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 up. And it just goes up and down, each one, and it creates its binary code. And on a lab scope, it would look something like this. Now, we'll get into more of the diagnosing of this stuff when we go to our next class, but this is a zoomed in CAN bus. You can see 2.5 volts, and at the same time, they just go up and down. That's as simple as it is. I should have just made this a 2-minute class. I could have been CAN bus. This is what it is, right? And here's kind of what it looks like between 2 modules. It's just 2 modules, 0, 1, 0, 1, 0, 1, and that's what we're looking for. But what the biggest part about my class is, how did we get there? If we just start testing there, or we know it's easy to know what to test for, but getting to the point where we need to get to is what we really needed to do. Let's look at another one, just so we can compare some of the differences. So we have KLine. And this is that KLine I was talking about, and this one transmits at 40. So you can see it's a little bit slower. And the protocol rests at 12 volts. That's good to know, because it's a completely different voltage, and it's pulled low to talk. So it looks like this. So now we have our protocol. It starts a one wire protocol, so it sits at 12 volts, and when it communicates, it pulls down to around 0 volts. So it would look something like this: 0, 1, 0. And I don't know if the ones or zeros in the right place, but you can see that protocols, no matter what they are, no matter what they're called, the only really difference is what voltage they start at, where is it pulled to, and what is it going to look like, or what should I test for? And maybe it's 1 wire, maybe it's 2 wires. And the speed is different too, but most of the time I really don't care about the speed, because I can't comprehend it anyways. Here's what that would look like on a scan tool. Starts at around 12 volts, and it pulls down, and it pulls down, and it pulls down. Now, there's a lot of protocols out there, and when I looked at the 5 OBD2 protocols, one of the biggest things I was trying to say is those are only the 5 protocols for the scan tool to the car. There's a whole bunch of different car protocols. There's FlexRay, there's MOSBus, there's a couple different kinds of CAN, there's all sorts of stuff. So I'm not going to talk about all those protocols, because it's not part of the process, and we're not going to remember all of them. I don't remember all of them. So what we have to do is we have to follow our process like this. We take the big network, we break it down to a smaller network, then we look how it's wired. And then once we know how it's wired, we're going to have to look up what protocol it is, because it changes so much. If I told you all the protocols now, they might change tomorrow, or the new car might change. So we have to kind of rely on our research. And this is kind of how we find it. So this is service information for a GM. And this is the high-speed CAN. You can see it starts at 2.5 volts. Adds 1 volt to plus, so 2.5 to 3.5, and subtracts 1 from the minus wire, the low-speed CAN. So 2.5, 3.5. Okay. And if you don't have service information, just Google it. This is an old Chrysler PCI bus. I just thought of some weird old bus just to see how easy it was to get protocol information. So I literally Googled, what is Chrysler PCI bus? This is why I'm not going to talk about all the protocols either. It's J1850, cool. Ooh, star configuration, single wire. I mean, look at how much information we're getting already. But here's what we needed to see. It's 7.5 volts when the bus is transmitting data. And I crossed the 0 out here. And 0 volts when it's silent. So just one quick Google, and we know it starts at 0 volts and it goes to 7.5 volts, 0 to 7.5 volts. So that's the easy part of this. So now let's look back at this for the last time. We see our diagram now. Now we can see that we have 4 small networks. We can see that this is ring bus. We can see that this is star, and this is a series CAN. And now we know that they're probably all on different protocols. Maybe this is the MOST bus. And maybe this is running just the normal CAN bus with 2.5 volts to up 3.5 to down to 1.5. And now when we look at this, I hope you can understand that this is the first 3 steps before we start testing. But guess what? Guess what we can do now? Now we can test. Now we're ready to test. And why this seemed like such a long process, once you put this process in, it's not going to take as long as my classes. You're going to get a car. You're going to quickly look at the diagram. You're going to break it down quickly. You're going to see the small network. You're going to bring it into what topology it is, and then you're going to Google the protocol, and within 20 minutes, you're ready to go. But you can see why we have to do this first. And now we're ready to test. And that's exactly what we're going to do in part 3. So I hope you liked what you've seen here today. If you did, hit that subscribe button, hit that bell icon so I can notify you when we get to part 3. And we're going to get some cars in. And we're going to follow this process. And I'm going to show you how it works. Again, thanks for watching. I'm glad you guys made it to the end if you're here. And as always, thanks for watching. So, Ryan with GoTech, signing out.